guys, this is just a very informal cell phone video explanation of all this mathematical kind of garbage that's going on. So, for the dark photon experiment, we need to know the mass of the muons. And so we need to get a formula that derives that. And so what we did was, since we're dealing with physics, we started with force analysis. So F equals ma is Newton's second law. And the details are not exactly super important to know. It's just essentially you have to start with that law that equates force with the mass times acceleration. And we know that for uniform magnetic fields, that motion, so we have uniform circular motion, something we call uniform circular motion. All that means, and all you need to know, is that turns the acceleration into v squared over r. And that's kinematics, it's mechanics. And then on the more E&M side of things, a force by a uniform magnetic field is qvb sine theta. Okay, so on the left side we have qvb sine theta, and since we have uniform circular motion, that equals mv squared over r. And if you do the algebra, you can cancel a velocity on one side, and solving and isolating m gives you m equals q beta r sine theta divided by v. Now, the way we have our detector set up is that we can get q, beta, and r and theta all from the way we have our detector set up, and I'll get into that at the end. But the main idea that you need to understand for the derivation is that the velocity, we can't just know the velocity, so we have to derive that velocity in terms of things we can get from the detectors. And that's where we come to the velocity derivation. So here's a little bit of math that to understand why we're doing this. So some other research was done, I think, by Sky and Joseph and Adriana, that they found these equations that the momentum relates momentum to the mass and velocity, and also to energy and the speed of light. So things that we can get. So the momentum, that y is a variable standing in for the Lorentz number, and then the m is mass, obviously, and velocity. And then we also know that momentum is equal to E over c in our case, because we're dealing with speeds close to the speed of light, like 99.9 something the speed of light. So basically we're just doing algebra again. We're setting these two momentums equal to each other, so ymv equals E over c. And the solving for the velocity, because once again, we just want the velocity to ultimately plug it back into that equation, right? So we get E over ymc. And so the way, this step here is a definition-based step. So the definition, mathematically speaking, of Lorentz is 1 over the square root of 1 minus v squared over c squared. And in this substitution, I kind of skipped the step showing you plugging in that fraction. Essentially, you reciprocate it, and you get E over mc times square root of 1 minus v squared c squared. Okay, so that's now equal to the velocity. Now, notice that we have a problem, right? Because there's a velocity on this side of the equation and this side. We need to get it on just one side. So that's why I did all of this algebra, essentially. You just square both sides to get rid of that radical, and then I distribute. This step is to distribute, so then I can then bring over the velocity term on the left side of the equation. And then you factor out those v squareds, and then you isolate. You get this kind of nasty fraction stuff. The reason why I pop this down is because you can take that m squared c squared term and throw it in the denominator so you get a cleaner numerator. What I'm going to do in the next step is factor this denominator. And that leaves you getting this. And then this little factoring trick is a little, I skipped one step, shows you exactly how I did this, but c squared and c to the negative 2. You have to read this as c to the minus 2 power. You can pull that out. And actually, if you go through and you distribute this, these two things are equivalent, okay? And the reason I did that is because then you can take that negative 2 and throw it in the numerator here. And now this is a lot cleaner, right? Compared to this, now we're here. So that's why we went to all this extra work. And then now we just throw that radical because we want v. We don't want v squared, we want v. And we get square root of this, and by just algebra, the EC squared is just EC, but then you can't simplify that addition of squares. So this is just radical m squared c to the 4th plus e squared. Okay, so that's v. Now we're not done. We got to stick that back into the mass equation. And then this will give us, and note that this is in terms of things we can get from the detectors. Energy, speed of light's a known physical constant. Mass, that's something that we're interested in. C to the fourth is, again, that's just speed of light, and then energy again. So this is all good to plug in. Once we get up to the actual mass derivation, we have the mass. So this is the equation. I just rewrote it from here so we know what's going on. So we have this, and then I rewrote the velocity thing we just did. So there's that. You stick the velocity now into the thing, and you get this fraction that is absolutely gorgeous. I rewrote it as in this form because this is going to make it easier to algebraically simplify. Notice again, it's very reminiscent of I'm going to square both sides, get the radical, and isolate the m's. And the reason is you can't have a formula where the mass is in terms of something and then there's a mass term. It doesn't work that way. So we're trying to get all the mass terms on just the left side of the equation. So once again, I square this thing out. This is no longer under a radical. And then what I'm going to do here is just to save like brain space. I'm going to assign a random arbitrary dummy variable to stand in for this. I mean, it's disgusting. If I had to write this down for the entire thing, I'd be sad. So the q beta r sine theta over ec squared. That is z. So whenever you see the letter z, that is filling in for this entire hunk of just number. So this then, notice that I'm going to then distribute between these things. So we have the m squared equals z, which is really just the shorter version of saying this, times c to the fourth m squared plus z e squared. And bringing the m terms to one side, because I'm going to do that same factoring trick, very reminiscent to what I did for the velocity, you end up getting this m squared equals z e squared over. Now, we can't keep it in terms of z, we got to throw back the whole shebang. So you get this fraction. I'm not even going to read it, it's just there. And this, and if you want to pause, I mean, if you catch an algebra mistake, I do not put it past me to make a mistake at this point. I've proofread it with a few people, and so far so good. But this is essentially what happens, and the reason you go between this step and this step is that this e is squared, but then you multiply by e squared, so that goes away. So that's why you have this q beta r sine theta over c, but that's still squared. And then over here, the c to the fourth is going to cancel with this c squared. So you'll have c squared in the numerator. So that's why I put that c and throw it down there under the squared term. And the e is still squared. So bringing that up here, we have, I now turn the 1, because I want common denominators so that I could fully simplify this fraction in the denominator here. And that gives me this. Okay, so the nice thing is the c is going to drop down, and the e squared is actually going to pop up. So that's how we get to here, is that this e squared term is now included in that square, and then this c squared, that c squared comes from this coming down here and being multiplied with all of this. And now that we have everything in terms of m, we just take the square root of it, and this is the master equation right here. The m equals eq beta r sine theta divided by c times the square root of e squared minus q beta r c sine theta squared. Okay, and I am going to then talk about why we can use this. Okay, so to calculate the mass of the muon, we need the following physical parameters according to this equation, right? And so the energy, which is represented by the capital E there, the energy of the muon is given by the calorimeter before the muon shield. So if you look at the experimental setup, be looking at that while I go through this, that might help kind of make things more concrete. Now the charge is represented by that Q, the lowercase q. Charge of the muon is given by the scintillator also before the muon shield, okay? And the magnetic field strength beta is that funny looking B. That's actually just a physical constant. That depends on the dipole magnet. In our case, that's going to be given by the BRM, which is a given that we'll have. So it's not a variable in our case. The radius by R, the radius of the muon's trajectory is going to be given by muon particle tracker. And the angle theta in that sine term, that's going to be the angle by which the muon is deflected. We will also get that from the particle tracker. And of course, the speed of light is just an unknown physical constant. We have all of the data. When we get all the data from these trackers and simulator or whatever, we'll be able to plug it in and get the mass, and then we will go forward from there. So there's the derivation for the mass of the Muon.